This is a Pentium 4. Here is an rtlsdr dongle with an R820T in the USB slot. I'm going to set up Linrad here and to set parameters to look at waterfall graphs with the highest possible resolution. I press U to do the setup, and here A first, and the rtlsdr, that's H. So there is only one rtlsdr, it becomes auto-selected. I set the lowest possible frequency in the high frequency range, that is 901 hertz. And then you didn't see that because I have selected fairly big fonts, so it's outside the screen. I select 0 for tuner and gain mode. This depends on the environment, where the interference is, if it's close range or wide range. And this is 144 megahertz. I expect the interference to be close to the signal where I'm listening to, and therefore I set it in sensitivity mode, that is 3. And I select the narrowest possible bandwidth because I'm going to look at narrow waterfalls. So that is 300 hertz, which means A. And the error on this particular dongle is something like 60,000 ppb, parts per billion, or 60 ppm. And then for the output I press B, and I don't use port audio, so I say no here. And then select the motherboard, that's 0. And X and W to save. And I'm going to look at beacons. I select normal CW, that's B. And here, what I select here will affect performance, and I will show that later. So to start with, I just press enter. So here is the default screen. I want to listen to the SK4 MPI beacon on 144.412. So I enter the frequency in this box here, 144.2. That's because I have selected the narrow filter, and the narrow filter is not at the center frequency, it's offset a little bit. So I press the arrow up here for the waterfall and main spectrum to get a narrower frequency scale or cover a wider frequency range. And then I go down here and set maximum gain. I can put 99 there, for example, and maximum turns out to be 66 for this dongle. Showing a little bit more of the spectrum and pulling it down, we can see this is the IF filter, and it's offset from the center 144.2, which is here, and we want to have the interesting signal somewhere in the middle of the passband. So it looks like this, 144.412. And the beacon is here. So I click on the waterfall above the beacon, like that. And it transmits a carrier for quite some time. I can see immediately that the gain is now too high. So I use this arrow here. And at this point I have to start to worry about the noise figure. There is a preamplifier in front of the dongle. If I switch it off, you can see the noise floor goes down quite a bit. So I can click on the noise floor here, and then I want the S meter, so I can move this a little bit to get rid of that. And then I make the S meter window bigger. And I want it in dB. And I don't want the peak, I just want the RMS noise, which is yellow. And now we can see when I switch off the preamplifier, the noise floor goes down by, how much is it? From here to here it is, well, we can evaluate that. Oops. 65.8. No. 65.8 to 50.6. That is 16 dB. That is a very reasonable increase of the noise floor. If I go for a little bit higher gain here, 51 dB, and then switch on the preamp, you can see that I have now 18 dB increase. That is a little bit more than necessary. The improvement in system noise figure would be 0.1 dB or so. That's not worth it. So I go down to, well, maybe 47. And I wait for the graph to go all the way to the left side of the S-meter window, so I can evaluate the level here. 69.2. See, that's 17 dB. This is good. One could use a little bit less gain if dynamic range turned out to be a problem, which it will not in my location. So I leave it like this and then switch off the S-meter, which I don't need anymore. You can see now that the signal, let's say the noise floor, is at 50 dB approximately. That's a very high noise floor. That is because this is an 8-bit AD converter, which means that the result is shifted by 8 bits at the factor of 256. So it's a good thing to go to the parameter menu, X, P, and change the first FFT amplitude here from 2000 to something like 256 times less. Maybe that's 8 or so. And then I press enter to keep the rest as it is. And I have to click the arrow here to bring up the spectrum to be visible. And I want to see details better, so I click here for the vertical scale. Something like this. And the interesting signal is 144412. And I have to switch on, of course, the preamplifier. I forgot that. So here and now I don't want to see a very wide spectrum anymore. I'm going for a close range waterfall, so I can click the arrows here to move the spectrum out, but I can also click in the frequency scale up here, and then I say I want to see the spectrum from 144 point, let's say 395 to 144.425 perhaps, and then I click apply. And here we have now the spectrum. And oops. And the purpose of this video was to show waterfalls. First of all, I can make this number here a little bit bigger. Maximum is 9. That saves CPU a little bit. Then I want to average more, so I press here and put a large number, let's say 200. And the number has to be a multiple of 9, because averaging is done in 2 steps. First, 9 spectra are averaged, and then groups of 9 spectra are averaged to get the final averaging. To continue, first I think I will optimize the first FFT parameters. You can see I have now 14% CPU load. X and P, and I try another first forward FFT version. 1. Third, 14%. No big deal. X, P, 2. What is good and what is not so good depends on the processor architecture. This is obviously quite a bit better. 10.7. X, P, 3. Not so good. 4. 10.5. Oh, this is the best one. Very good. I will leave that. X, P. Now, to get a high resolution waterfall, I need to enable the second FFT. And you can see, now we have problems. It gives a lot of load to the CPU. I press T. So this is not okay, we are losing data. And now it says sync error, and now it says something else. It's simply overloaded, so I have to do something else. B and X, P. First backward FFT version, I make it 1. That means use the MMX routines. And also I make a easier window, a sine window instead of sine squared window. And then click on the signal. Where is it? 412. And now you can see there is no problem with CPU overload anymore. But I have not yet set the optimum parameters for visibility in the main waterfall. That's not necessary. I can be satisfied with only the baseband waterfall, and then I don't need the second FFT, and that saves a lot of resources. But I can try to get the high visibility waterfall also in the main spectrum. X, P means I have to reduce the bandwidth. Here it's now 20 Hertz, and I might want 10 Hertz, so I make this 3 instead of 2. Bandwidth 10 Hertz. And there was an underrun error once. And we can see that the dominating load is the second FFT with 61% of a core. X, P. I try the MMX for that as well, that's number 2. And you can see that's worst. It's not better. It's worse. So, no good idea. X, P. And there is another floating point algorithm, number 1 here. This seems to be the optimum in this situation. So to look at the waterfalls, first switch off the timing information, T, and then rearrange the screen a bit. I don't know really how I want it. It's easier on a bigger screen. This is just a 1024 by 768, is it? I can move this thing here. And I don't know where the frequency control window is. I may have hidden it below something, so I make X and B. And here we are. And here is the beacon. The waterfall has an averaging of 36. And since the resolution is about 10 Hertz, it means that I get something like 10 lines per second, so this is 3 seconds per waterfall line or so. To make the gain much larger, 4, and then I have to set the threshold a bit higher. Well, I can right click on it. Well, I have to put the value there and then right click on it, and then it is supposed to auto set. I had to right click a couple of times. Now we have a very sensitive waterfall up here, and you can see not easily. We have 10 Hertz from here to here. I will temporarily widen this window. The high resolution window here is drawing the waterfall with 1 pixel for each FFT bin. The optimum visibility comes if I expand this window for the same scale as I have here. It means, oops, I don't know what this is. This is something probably because the computer is loaded very close to what is possible. It's clearly a bug, 55233. The selected frequency comes outside the window that is shown when I did that expansion. It doesn't happen often, I haven't seen it before, but it can be corrected someday if it happens more often. Now I have the same frequency scale in the main waterfall and in the high resolution graph. And you can see the frequency is drifting rather rapidly. That's because the temperature changes when I switch on or off the processing in the dongle. You will see that it will stabilize within 10 minutes or something. The averaging in the high resolution graph should be much bigger. Let's make it 200. And then we can see the beacon. in 10 Hz bandwidth. And how it's drifting. The signal 200 Hz up is a signal generator. Is it? No, it's not. I don't know what it is. Let's listen to it. Oh, that's the beacon. And the other signal is some spur. Now the next thing is, I don't want to see too much of that, but I do want the waterfall from the baseband, and I would like to have a wider screen for the baseband, so I will now change the font scale. Now the font scale is 1, and you can see that the waterfall scale is the same in the main waterfall here and in the baseband waterfall. That's not what I want. So X, P, first mixer bandwidth reduction, it's now 7, that's 128 times. I make it 8 times larger, that means 10, or make it 16 times, that's 11. And click on the signal again. And now I have to reduce the averaging because the transforms are really big in time. Let's say average of 5. I right click the 0 point a couple of times. I don't know why the gain changed, and you can see drifting goes far more rapidly here. And I will leave this running for a while. Now I changed the font scale to 1 and waited for a while. I also rearranged the screen a little bit. Here is the beacon SK4 MPI. Here is something moving and creating reflections. And there was something about 1.5 minutes before. Maybe this is a meteorite. It lasts for a very long time, but I don't think airplanes would last for such short times as this and not change the Doppler shift so rapidly. I have added a signal generator nominally 100 Hz above. Errors are there, so it is now about, is it 40 Hz up or something. That signal generator has a perfectly stable level, so I can tune the level down by inserting some attenuation. I now insert 10 dB, and we won't hear the beacon anymore, and it's weak today. Yesterday, when I made the first part of this video, the beacon was very strong. And we will see now that here 10 decibels on the signal generator makes it very weak. And it's not visible up here anymore. Even if I change the color scale a bit, I like this 24.2 for example. Okay, then we can see it. No, sorry. There was some memory effect that I forgot about. We cannot see it anymore. And here maybe, but very weak. What I can do now is to expand the frequency scale in the baseband by a factor of 2. No, the limit is baseband storage time. I have to change that. X, P, and enter. Second FFT storage time also has to be big enough for the transforms used in the baseband. So I make this 20 seconds. And the baseband storage time, this doesn't cost anything, so I make it 60 seconds. The sampling rate is very low. And here is the beacon. And the screen was invalid somehow. So I have to move this window again. And then I have to wait for a while. After increasing the storage times, I should be able to expand the baseband waterfall 2 times, 4 times, 8 times, and then I turn back to 10 decibels so I can see immediately where things are. I also change the averaging to have no averaging in order to make it not very slow. And here is the beacon, here is the signal generator, but it's not attenuated. Now I have to wait for a while and then look what happens when I do the attenuation. Because I made an exit and then a return, and that changed the current through the dongle for a while, so the temperature is now unstable. I have to wait for it to stabilize. Now the frequency scale is expanded and we have the beacon here with keying sidebands, and you see the keying here, and then my signal generator that is injected about, well, nominally 100 kilohertz above, but you can see it's about, 100 hertz, but you can see it's about 40 hertz really. And now add 10 dB attenuation on the input here. And it will be difficult to hear the beacon. It's not very strong now. Well, I can hear it, but weak. Now that the resolution is much higher, it should be possible to see the signal generator even though it's attenuated by 10 dB. You can see the instabilities here. That's the phase noise. The signal is not really as narrow as the resolution of the FFT. But and a more stable receiver than this dongle would make the signal more visible and would allow some averaging to make it stronger, and maybe it would be possible. Yes, it would. I can make the waterfall a factor of 2 slower by putting 2 here. And that should improve visibility a little bit up here. I will leave this running for a while. Now some time elapsed with the 10 dB attenuation. It's quite clear that the frequency stability of my signal generator here and the beacon here is different. The dominating problem is the frequency drift of the dongle, but the frequency drift from here to here is twice as large as the drift from here to here. And I don't know really what the absolute frequencies are. Now I add 3 more decibels of attenuation. Like that. And it will take quite some time before the consequences will be visible, so I switch off here. Now the total attenuation is 13 dB. This here is the point where I added 3 more decibels. Then I shifted the frequency here because things are drifting, as you can see. The signal is still quite well visible, so I add 3 more decibels of attenuation. And I'm looking for the limit. And the signal generator is stable, so I can compare this with other things later on. Having established the weakest signal that can be detected with this USB dongle, that is because of the stability limitation. It's here, and that's the signal generator. 3 dB more and I wouldn't see it anymore. This is where it comes from. I increased the level from -120 to -90. That is 30 decibels more. Now the signal is strong enough here, so I can measure the signal to noise ratio. And to do that, first, to make it quicker, I change the resolution and set the bandwidth to, let's say, 100 Hertz. I can see it better if I move this line up there. This is a bandwidth of 100 Hertz. And I want the S meter. And only show the RMS That's this. Sorry, I want dB and RMS. And then I switch off the signal just by tuning where it isn't. And you can see the signal plus noise to noise is very small. So I add 10 more decibels. So signal plus noise is here, 52.6 dB, while the noise floor, I have to wait a little bit more. Is here, 41.8. So S plus N divided by N is 10.8 decibels. That is 12 times. And that means S over N is 11 times, or 10.4 dB. So the correction from S plus N to S over N is only 0.4 dB. And that is in a bandwidth of 100 Hertz. So in a bandwidth of 1 Hertz, the signal to noise ratio is 10.4 plus 20, which is 30.4 dB. And the weakest signal is 40 dB below this. 30.4 minus 40 is minus 9.6. The noise floor is very close to minus 174 dBm in 1 Hertz bandwidth, because the low noise amplifier has a noise figure of I don't remember exactly, 0.15 decibels or something like that. It's practically zero with the accuracies we talk about here. So the weakest signal is 174 plus 9. 174 plus 9.6 is minus 183.5. That's the signal level. Let's make it minus 184. I skipped the decimal. Minus 184 is the limit for this system. To put it in perspective, the noise floor in SSB bandwidth 2.4 kHz is minus 140 dBm. The weakest signal detected with JT65, it's 28 decibels below that. But the limit we have seen here is 44 decibels below that, which means the signal is about 16 decibels below the detect threshold for JT65 in deep search mode. So it's a really weak signal. I have now established the sensitivity. The next important thing is the dynamic range. To get an idea about that, I will look at a wider frequency range. I click inwards here a couple of times from both sides to cover a bit more than 100 kHz, and then I switch on a signal generator. You can see it comes up here, and then I can press A, and we can see the amplitude margins. It's 16 decibels. And now it's 1 dB below saturation. And the frequency separation is small, but the noise floor did not change. It's easier to remove the second FFT when measuring signal to noise for a strong signal. So I make this 0. And I increase the baseband sampling rate by a factor of 16, going from 11 to 7 here. And turn up the signal generator again. Here we are. And I press A to see the amplitude margin again. So here is close to the point of saturation by 1 dB. And you can see the quality of the signal generator is limited. This is the other signal generator, which is stable in frequency. The level for the signal that is close to saturating is 75 dB. I make the bandwidth 500 Hz. It's well, like that, 500 Hz bandwidth, and of course the signal level doesn't change when I change the bandwidth. The amplitude has drifted a little bit. It's the stability of the dongle, I guess. So we have here 75.5, and the noise floor, I change the frequency of the generator. And then I can read the noise floor here, 22.7. So this gives a dynamic range in the standard bandwidth of 500 Hz of 75.5 minus 22.7, which is 52.8. And the decimal doesn't mean anything, so I say 53 decibels. And which means that the signal is, I have to add 27 to get it in 1 Hertz. So it means the signal is 80 decibels above the noise floor in 1 Hertz. And that's where the dongle saturates now. When it is set for maximum sensitivity, it means the gain up here is set to 47 dB. I will now reduce the gain until there is a 1 dB loss of sensitivity, and then look at the dynamic range. I have increased the bandwidth and I have increased the signal level. That is to make things run faster. The signal is at this level, 56 roughly, 55.6. And the noise floor, I click just a little bit on the side, it is at about 31, so it is very far below. .7. And then I try other gain settings and then compare signal and noise to find at what gain setting do I have a 1 dB less sensitive system. This is the result. It looks like a good setting would be 29. This is only half a dB below what I had at 47. So I set 29 here and then go for the sound card test mode, that's I, and then I press plus a couple of times, and here you can see the gain is too low. I have only 2 bits reasonably often populated, so I have a high level of quantization noise, and this causes some odd phenomena. So I look at the level of the signal generator and then I inject another signal. You can see here, and that affects the level in a maybe odd way. If I click on the noise floor and then I remove the other signal generator, you can see that the noise floor is a little affected. So this would be okay if there is a big problem with interference, but I think it is more appropriate to go for a little bit higher gain here. 32, and once again 32. This is now from 6 to 12. It is 6 decibels more. X, and sound card test mode I, and plus. And now you can see we are having a signal that spreads over 4 states of the AD converter. That is very good. Maybe a little bit more than necessary, so I go back X, and B, and set the gain to the other 32 decibel gain level. This is something that might be changed in the rtlsdr library to not have them writing the same gain level in this case. I can now look at the dynamic range. That is, how strong can a signal be above the noise floor before saturation happens. So I look at the noise floor, I right click in this box, so here we have the noise floor, and press A, and then bring up the variable signal generator, the frequency variable thing, and you can see the noise floor goes up, and we have artifacts. That is because there are so few bits. And here is saturation. And I move the frequency a little bit because we have sideband noise from the signal generator. Disconnect the signal. So you can see when the strong signal is running, there are phenomena, this spur and that spur, that disappear. That's because we are using so few bits on the A to D converter. It's a little bit hard to really say what the dynamic range is, but I can make an attempt to guess it. The bandwidth is now 500 Hertz. The signal level is here, 75 dB, very similar to before, because I haven't changed the gain. I only changed the analog gain, which means that when I disconnect the signal, the noise floor is going to be lower than it was before. And you can see here that the noise floor is much lower than the floor was when the signal was also present. I need a better signal generator, and probably the problems I can see here are because of the phase noise of the dongle. Oops. Well, this doesn't look well like that. So the level is now 0.9 dB. It means 74 decibels signal to noise in 500 Hertz bandwidth. It's a huge improvement. But we have this problem of having very few bits in action. Now I have injected a good quality crystal oscillator at 144.048, and the level is 76 dB, 76.7, and then I look at the noise floor close to it, let's say here, and it's low. Here is the noise. And then I disconnect this strong signal. And as you can see, the noise floor didn't change. What I measured previously was the sideband noise of the signal generator. But if you look at the waterfall, you can see there is a small change of the noise floor. The waterfall has gain level of 4, so it's very sensitive. And I could see that probably by comparing this 1.90 to this 1.77. So there is 0.1 dB roughly. So the dynamic range is 1.9 to 76. That's 74 decibels. That's the number I arrived at before, actually. Running the dongle at 900 kHz causes a lot of CPU load. It's marginally possible on this computer. I now change to run it on 300 kilohertz, and everything else the same. Sensitivity mode and A, and the error was 60,000 ppb. XX, save that, and then go for normal CW V, and number 4 will still be fastest, although it doesn't matter much anymore. Storage time, I think 20 seconds, and 8. And I don't enable the second FFT now because I'm just going to look at dynamic ranges. Bandwidth reduction 1 is very little. We have 300 kilohertz. Let's say 4. And the signal is now this crystal oscillator at 144.048, if I remember properly. I don't know where the frequency control window went, so I make X and then V, and here it is, 144.05. And here is the strong signal. And I have to repeat this measurement of signal to noise ratio at different settings on the gain for the dongle. At 300 kilohertz we have 0.5 dB loss at the gain setting of 40 and 0.8 dB at the gain setting of 38. At 900 kilohertz we can go down to maybe 38 or 32 to get the same kind of signal to noise ratio loss. So I try 38 and then XX and I, and there's a new sampling rate, and I press plus to magnify, and you can see this level is larger than necessary. We have more than 4 bits on the AD converter. Oops, don't know what happened. B. There are still many little errors inside Linrad, but normally just exit and restart and it will be good again. So I cannot go down to a lower gain because the signal to noise ratio will lose more than 1 dB. So I have to stay here, and this means that the dynamic range is going to be not quite as good as it was with the higher sampling rate, and I will verify that. I've now set the good crystal oscillator to 1.4 dB below saturation, and the level is 77 dB, as you can see. And the noise floor is here, and I have to wait just a little to see what it becomes, but it's about 10 dB. Now I think I can get a number. It's 9.1. And that is a dynamic range of 67.9. Or let's make it 68. I had 74 at the higher sampling rate, and I have lost 6 decibels by reducing the sampling speed from 900 kHz to 300 kHz. If you don't need those 6 decibels of extra dynamic range, then of course run the dongle at 300 kHz or maybe even at 230 to make processing far less critical on slow computers. This is economy settings for a slow computer. The load, as you can see down in the left corner here, is less than 5%. The beacon SK4MPI is here, and the signal from the signal generator, which is now 10 decibels below the noise floor in 1 Hz bandwidth, is the same level as I showed before, and we can see it, but in the main waterfall we see nothing, because the second FFT is disabled and the bandwidth of the first FFT is too large to allow anything to be seen in the waterfall at the low levels that we are looking at now. So I hope this video has shown a little bit about all the possibilities you have with Linrad. Things can be set in many different ways depending on what is the problem you have. Even an rtlsdr dongle can provide a very large dynamic range. At 900 kilohertz it gives 74 decibels dynamic range in 500 hertz. That is 74 plus 27 is 101 decibels of dynamic range in 1 Hz, but the weakest signal we can see is 10 dB below that. So we have a dynamic range of 111 decibels. That's quite impressive for a dongle that costs next to nothing.